Okay, so here's where we are heading into new territory when it comes to our quadratic algebra. So most of what we've covered so far should have been familiar from last year, so reviewing expanding brackets and factorising quadratics and using the null factor law to solve quadratic equations. So now what we want to have a look at is what are some of the options if the quadratic equation does not factorise? Okay, because that's perfectly possible. It's perfectly possible that there would be factors of the last number that don't add up to the middle number. Okay, and so one of our options involves completing the square. So in this video, I just want to introduce the process of completing the square. It is a possibility to use when you are solving quadratic equations, but actually the method we'll introduce in a couple of lessons' time using the quadratic formula for me is preferred over completing the square for solving an equation, and that's because the quadratic formula is completing the square. It's just a formula for that. However, when we look at graphs of quadratic functions in semester 2, there is a significant need to be able to complete the square when we're thinking about the graphs, because it enables us to turn the equation into a more helpful version of the equation for graphing. So the technique is important beyond just solving equations. So today I want to have a look at how we complete the square and what that is, and then in the next video we'll look at how we might use completing the square to help us when solving quadratics, but then after that I'll look at how we use the quadratic formula when solving quadratics, and personally I would use that as a solution method, the preferred solution method if your quadratic equation doesn't factorise. But as I said, there's very good reason why we need to learn how to complete the square for all sorts of other things, and it's actually not just about graphs of quadratics, it comes into thinking about graphs of circles and all sorts of other things down the track. Okay, so what we need to first of all refresh is our understanding of perfect squares, because completing the square involves creating a perfect square where we don't otherwise have one. Okay, so a perfect square is a quadratic expression that's written in the form a plus or minus b all squared. So for example, x plus 2 all squared, 2x minus 3 all squared, 7 minus 3x all squared, etc., etc. All perfect squares. So we might remember that when we expand perfect squares, they look like this. If we have a plus or minus b all squared, we get a squared at the start, we get b squared at the end, and then we get plus or minus, depending on whether there's a plus or minus in the original bracket, 2 times a times b in the middle. Okay, so when we recognise the patterns in the perfect square, it is quicker to factorise. And so we want to be able to factorise when we see perfect squares, but we in particular want to be able to identify the patterns that go on here for our process of completing the square. Okay, so let's have a quick look at these couple of examples with perfect squares. So solve each of the following. We would again try and use our null factor law. One side's equal to 0. We want to factorise the other side. And in this instance here, you'd be looking for factors of 9 that add up to -6, and they are -3 and -3. And so therefore this factorises to x minus 3 all squared equals 0. Okay. Now, you might want to, you might still use your normal quadratic trinomial factorising process for that, or you might be able to see this pattern, and that's what I want you to try and get a bit better at. So x squared, here we have minus, it is 2 times 3 times x, okay, and then this is 3 squared at the end here. And so what we have is that perfect square pattern, which means it is x minus 3 all squared. And so therefore x minus 3 equals 0, so x equals 3. In the one on the right, it's a non-monic or harder quadratic, so if we wanted to factorise it, it would be a lengthy process involving 9 times 4 factors of 36 that add up to 12, etc., etc. However, if we can recognise the perfect square pattern, and what I'm looking at here to trigger it is that the first term is something all squared and the last term is something all squared, and so then I'm trying to check, does the middle term follow that? So I'm seeing here that the first term is 3x all squared and the last term is 2 all squared, and so therefore this would be a perfect square if the middle term is 2 times 3x times 2. Okay, if that's what's in the middle, then we have a perfect square, and yes, 12x is 2 times 3x times 2, and so therefore this is a perfect square that is 3x, the plus because of the plus here, and 2, so 3x plus 2 all squared. So 3x plus 2 equals 0, 3x equals negative 2, and x equals negative 2 on 3. Okay, so as I said, there's a technique called completing the square, which allows us to convert a quadratic equation from this form. Sorry, let me get a highlighter so you can see what I'm talking about. Sorry, let's just choose a yellow one. Okay, so from this form into this form. And this is useful when we're solving equations, but this is also really useful when we're graphing and when we're doing all sorts of other things. Inverse functions next year, all sorts of other things. There are reasons why we need to complete the square. So the aim is to convert from that form into that form. Now the reason the second form, this one, is great is because we can solve that by rearrangement, which we looked at a few videos ago. Okay, we don't need any special techniques to solve that. We've just got x in the one place in the equation, and so we can subtract k, divide by h, divide by a, take the square root and add h, and we've then got x on its own. And so that's the point. We want to take a quadratic in this form and turn it into a quadratic form which can be solved by rearranging. Okay, that's what we want to do in completing the square. That's why it makes the solving process easier. We're only going to do this though if the original quadratic factorised easily, then we wouldn't bother with this process because we could factorise and use null factor law. If it doesn't factorise, we want to turn it into this so we can solve by rearrangement. Okay, so in order to complete the square, the key process of completing the square is the perfect square. We're trying to make something that isn't a perfect square, take something that isn't a perfect square, and to rewrite it using a perfect square. So we see that in this form here, we've got this perfect square sitting in there. Okay, so we want to create that perfect square, and then the other things will just fall into place around it in order to keep it still the same as the original quadratic. So it's important that we can see the patterns in the perfect square expansion. Okay, so there's a number of things happening here. The first is that this is what's key, the coefficient of x, okay? And if we want to get from the coefficient of x, which is positive or negative 2a, to the constant term, which is a squared, the process that we're going to need to do is to halve that number, plus or minus 2a. When we halve it, will become plus or minus a, and then when we square plus or minus a, we'll get a squared. Okay, so if you take positive or negative 2a and you halve it and then you square it, you get a squared. Okay, so we want to halve and square the coefficient of x to produce the constant term that will make a perfect square. Then once we've made that perfect square, to write it as a perfect square, we just want to halve the coefficient of x. Okay, and it's better to think about halving the coefficient of x rather than square rooting the end term, because square rooting the end term doesn't tell you whether it's positive or negative. So if you've got a positive coefficient of x, it'll be x plus something all squared in the perfect square. If you have a negative coefficient of x in the expanded version, you'll have x minus something all squared. So the key thing is halve and square to get from the coefficient of x to the constant term in the expanded version of the perfect square, and then to actually factorize that, we're going to halve the coefficient of x. Okay, so the question here is, or a series of questions, what must we add to x squared minus 12x in order to produce an expression that is a perfect square? Okay, so if we've got x squared minus 12x, the question is, what would need to go on the end here to make it a perfect square? And we know that if we take this coefficient of x squared, negative 12, and we halve and square it, we're going to get something that makes a perfect square. Okay, so halving negative 12 is negative 6, and squaring that is positive 36. And now what we have here is a perfect square. Okay, and in fact, let's take it a step further and write it as a perfect square. So what would that be all squared? Okay, it's going to be x, and then it is half of the negative 12. Half of negative 12, so it's x minus 6 all squared. Okay, all right, let's think about the next one. I'll write it in under here. Okay, so we've got x squared plus 2x. What do we have to add on to that to make a perfect square? So we're going to have x squared plus 2x. The question is, what goes on the end here to make that a perfect square? And then finally, what will that perfect square be? Okay, so again, it's about positive 2. If we halve and square that, we'll get something that will follow the pattern of the perfect square. So half of positive 2 is positive 1, and squaring that is positive 1. So x squared plus 2x plus 1 is a perfect square, and it is x plus 1 all squared. Okay, so remembering halving that positive 2, so because it's positive, we get positive in the bracket here, and it's x plus 1 all squared. Okay, what number must we add to x squared plus x to produce an expression that is a perfect square? Okay, so remembering that this is 1x, so halving and squaring 1. Okay, I'll write off to the side here. If I take the number 1, positive 1, and I halve it, becomes half, and I square it, I get quarter. Okay, so if we add 1/4 onto here, that's now a perfect square. X squared plus x plus a quarter is a perfect square. And when we write it as a perfect square, we take that positive 1 and we halve it, which will make it plus 1/2. So we're going to have x plus 1/2 all squared. What number must we add to x squared minus 3x to produce a perfect square? Okay, so again, halving and squaring negative 3. Right, so think about that. Negative 3 half and square will become 9 on 4. Okay, so we're adding 9 on 4, and that's a perfect square. X squared minus 3x plus 9 on 4 is a perfect square. All right, and then we want to take our negative 3, sorry, not negative 3x, just the negative 3, and halve that, so minus 3 on 2, to work out what's going to go in here. So x minus 3 on 2 all squared is that perfect square. Alright, so the idea of creating the perfect square out of something that isn't in order to complete the square. Alright, obviously what we've created something completely different here, so we now need to talk about, well, how do we balance that out? We can't just magically add 1 in because we want to make something a perfect square. How do we make sure we're not actually changing the value of the thing? Okay, so we're going to show that through some examples. So complete the square for each of the following quadratic expressions. Okay, so the idea is, at the moment it's not a perfect square. If I halve 6 and square it, I would get 9, not 8. So this isn't a perfect square. So what we want to do is create a perfect square. So x squared plus 6x, we want to turn that bit into a perfect square, and then we'll worry about the plus 8 at the end. Okay, we'll just leave that for now, we'll think about it later. Let's focus on the first two terms and how we make a perfect square out of that. So, halving and squaring plus 6, half of positive 6 is positive 3, squaring that is positive 9. Okay, now we're trying to suggest that this is equal to this, okay? But it's not equal anymore because I just added 9 to it because it suited me to do so. So I also need to take away 9 because I actually haven't changed anything. I've just rewritten it slightly in a way that's going to be helpful given that that's what I'm interested in. Okay, so those first three terms, they're my perfect square. X squared plus 6x plus 9 is x plus 3 all squared, remember, halving that. And then outside of that perfect square, I now have minus 9 and plus 8, so minus 1. Okay, so we have now written x squared plus 6x plus 8 as x plus 3 all squared, take away 1. And the advantage of the second version from the first version is that if I was solving that equal to 0, I wouldn't need to factorise. I could just add 1 square root and take away 3. Okay. Now, part A, if we were solving this equation equal to 0, it does factorise, so I would factorise and use the null factor law rather than complete the square. But we're looking, this is a technique that's going to work even if the quadratic doesn't factorise. So when it doesn't factorise, we would then want to go to this. So for example, in part B, factorising factors of negative 6 that add up to negative 2, they don't exist. So converting this quadratic into this particular form via completing the square would be a way that we could go on and then solve that. Okay, so let's have a look at part B. So this quadratic expression is equal to x squared minus 2x. We want to add and subtract something in there so that we're making a perfect square, and we'll just leave our negative 6 sitting over there. Okay, so halving and squaring negative 2. Half of negative 2 is negative 1, and negative 1 squared is positive 1. Okay, so we want to make, there's our perfect square, but we can't just add 1 in because we feel like it. We've now created something that isn't equal anymore. okay, and that's a problem. So we want to also take 1 away. All right, so, oops, sorry, lost my pen. Okay, so perfect square. Oh, everything's going crazy here all at once. Okay, here we go. All right, so that's my perfect square, and that is x minus 1 all squared. All right, and then let's focus on what we've got that isn't the perfect square. We've got minus 1 and minus 6 out here, so minus 7. So I've completed the square. X squared minus 2x minus 6 is the same as x minus 1 all squared, take away 7. And as I said, we could then solve that by rearrangement if what we were trying to do here was solve the equation. Okay, part C, let's have a look at this same process again. So same idea, x squared plus 3x, that's going to form the beginning of our perfect square. We need to work out how to end that perfect square to make it a perfect square, and we'll leave that negative 5 over there. Okay, remembering that these two things need to be equal, so anything we add in we also have to take away. Alright, halving and squaring. So remember, half of 3 is 3 on 2, squaring that is 9 on 4. So we want to add 9 on 4, which means we need to also take away 9 on 4. There's our perfect square there, those first 3 terms. It is x plus 3 on 2, remember half of that, all squared. And then outside of here we've got minus 9 on 4 and minus 5, so common denominator. You might be able to do it in your head. I'd like you to try and get a bit better at working with fractions in your head, thinking about 5 as being 20 on 4. So what we have is minus 9 on 4 minus 20 on 4, so that is minus 29 on 4. And there we have completed the square. Okay, so x squared plus 3x minus 5 is the same as x plus 3 on 2x minus 29 on 4. And I know we've created fractions, but the advantage here is if we were trying to solve this equation, this doesn't factorise, factors of negative 5 that add up to positive 3. So therefore we could convert it to this and then solve by adding 29 on 4, taking the square root, and subtracting 3 on 2. But this question isn't about solving, this is just about completing the square. And as I said, we have many situations where we need to complete the square for reasons other than solving, first and foremost of which is if we were trying to sketch a graph here, and this would be a helpful way to do this. Okay. This technique only works for monic quadratics. Okay, so if you have 2x squared, negative x squared, 5x squared, 6.8x squared, you have to divide that number out before you can complete the square. Okay, that's really important. It's the number one place where you'll go wrong. Okay, so the fact that we've got a 2 here in this example, we cannot complete the square at the moment. So we have to factor out the 2, even if it means making fractions. The first step has to be to factor out the 2. So we get x squared plus 2x. We're then going to try and complete the square with that, and we'll have 9 on 2. Okay, so now let's focus on the completing the square. Halving and squaring 2. Half of 2 is 1, 1 squared is 1. So adding 1 makes that a perfect square. We need to take away 1. Now, the next thing I want you to be really careful about here is not losing the 2 and the fact that everything inside those brackets needs to be multiplied by 2. This is the next place you'll go wrong. You either won't factor it out at the beginning, or you'll factor it out, but then you won't multiply it back in properly at the end, because you'll have lost track of what's being multiplied by 2. Okay, so really clear about that. Don't lose track of that. Start off, I've got 2 times everything in here, and let's just work on what's happening in here. Okay, so perfect square is there. It is x plus 1 all squared. And then we've got minus 1, which is minus 2 on 2, plus 9 on 2. So negative 2 on 2 plus 9 on 2 is plus 7 on 2. Alright, so we can bring in that purple bracket a little bit. Okay, so this is where it's key. This is where, at that step, you'll have forgotten to write those purple brackets, and you'll therefore have the incorrect answer. Because what needs to happen now is, we now multiply out these purple brackets by doing 2 times this bracket, and 2 times 7 on 2. And so when we do that, we get 2 lots of x plus 1 all squared plus 7. And we've completed the square. Okay, part B. Again, non-monic. So the first thing we must do is factor out the 3. So again, let's be clear about, take it out. Everything in there is going to be multiplied by 3. We focus on completing the square in here. And then at the end, we multiply everything by 3 again. Alright, so this is now going to become x squared plus 2x. We have to work out our perfect square, and then we've got minus 13 on 3 at the end here. And again, we'll worry about that later. Okay, halving and squaring 2 again. So half of 2 is 1, 1 squared is 1. Okay. And so there's our perfect square in those first 3 terms, but all of that is within our purple bracket with the 3. Okay, so x plus 2x plus, sorry, x squared plus 2x plus 1, it's a perfect square, it's x plus 1 all squared. And then outside of that bracket, we've got minus 1 and minus 13 on 3. Now again, I want you to try and get better at doing the fractions in your head. Negative 1 is negative 3 on 3. So we've got negative 3 on 3, take away 13 on 3, so negative 16 on 3. Okay. And then again, final step now is to multiply the purple 3 back in, get rid of those purple brackets, and so we're going to get 3 times x plus 1 all squared minus 16. Now again, can we just have a quick look at that? 3 times 16 on 3, you shouldn't be doing 3 times 16, okay? The 3's cancel out and it is just 16. If you've got 16 divided by 3 and then you're multiplying it by 3, it's just 16, okay? Don't go to 48 on 3 and then have to simplify it. You should be able to see that that's just 16. Okay, part C, again, we've got non-monic, so the first thing we need to do is take out the negative 2, okay? Even if it was just negative x squared, you have to take out the negative. Anything other than positive 1 as a coefficient of x squared needs to be factored out. Okay, so we've got x squared, it's going to be minus half x, sorry, it'd be plus half x, we've taken out negative 2, and minus, sorry, I'll leave room for my perfect square there, and then we're going to have minus 21 on 2. So we've halved everything in there. We want to halve and square, okay? If you take half and you halve it again, it's a quarter. Half of a half is a quarter. You double the denominator, and then we need to square that, which is 1/16. Okay, so plus 1/16. And we also need to take away 1/16, so it's still the same thing. First four terms are our perfect square, okay, and they are x plus half of a half, so it's a quarter squared. And then outside of the bracket, we've got 2 fractions there, negative 1 on 16 minus 21 on 2. You can take a moment for common denominator if you need to. Negative 1 on 16 minus, we're going to need to times top and bottom by 8 here to get a denominator of 16. So 8 20s are 160, 8 1s are 8, so 168. Okay, so let's just put those fractions together. Again, don't lose the fact that you've got negative 2 times all of this, negative 2 times all of this, okay? So we've got x plus a quarter all squared, and then minus 1/16 minus 168 sixteenths, so that's minus 169 sixteenths. Okay, so now we want to expand back out that purple bracket, negative 2 times the bracket, and negative 2 times that fraction. So it's negative 2 times x plus a quarter squared, and then negative 2 times negative 169 on 16, so it'll be positive. And rather than do 2 times 169, we recognise that the 2 will cancel down with the 16 to give us 169 over 8. Okay, it'll always cancel down with the denominator. You should always be cancelled when you multiply that number that you've taken out. When you multiply it back in at the end, it should always be able to cancel down with the denominator. Okay, so we've taken our original quadratic and now written it in this form by completing the square. So the work today is on a worksheet, just focusing on the process of completing the square, and then in the next video we'll have a look at, once we've completed the square, how it's a useful method for solving a quadratic equation.